Okay, Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So in this session, I'm going to talk about the 2.6 block diagram models, which is one of the subtopic under the mathematical modeling topic 2. And in our previous session, we have discussed about the transfer function. Yeah? So transfer function. So basically, the transfer function that when we design the control system, so we'll start with developing the mathematical model that, and then use the Laplace transform to transform it to the Laplace domain, and then get the transfer function, which is the ratio of the output variable to the input variable of the Laplace transform. So for that transfer function, GS, for example, what we do is we put it in the block. We try to represent the process based on the transfer function by using the block diagram. So in this session, we are going to explore about how we can use the block diagram to represent the control system model. So in our beginning of the topic 2, we were discussing about the open loop control system and also the closed loop control system, which is inside that control system, basically we have not only one, but more than one block, more than one block that represent the model of the system, whether it is the actuator, the sensors, feedback sensors, or maybe the controller, right? For example, the valve is one of the example of the controller, right? So for that particular control system, most of the time we will deal with the closed loop control system. We will use the block diagram model. Okay. So we know that in control engineering, we commonly use a diagram which is called as the block diagram. So what is the block diagram itself, right? A block diagram, as you can see in this slide, block diagram is a system of a system is a pictorial representation of the functions performed by each component and of the flows of the flow of signals. I mean that we have block with the flow of signals, input and output signals. Such a diagram depicts the interrelationship that exists among the various components, differing from a purely abstract mathematical representation of block diagram has the advantage of indicating more realistically the signal flows of the actual system. And then in the second paragraph here, as you can see, in a block diagram model, in the block diagram, all system variables are linked to each other. Okay, so we have many models of actuator model, processor model, and then also processor and also the actuator model. So there are many functions in there. So there are variables, the variables that link together, that link each other. So from one variable to another variable, okay, that variable is connected to each other through the functional block. Okay, so the functional blocks, or simply we can call it just block. Block means that block with function. Okay, so that block is a symbol for the mathematical operation on the input signal to the block that produce the output. Okay, so let me start by explaining about how do we represent the block diagram. How do we represent the block diagram? As basically, we'll start with the function GS. Okay, GS. I have this function, and I have input of x, and also output of ys. Okay, so I have that input of xs in the form of Laplace transform that will output ys, and gs is my transfer function. So to represent it using block diagram, I just put the gs inside the block, And here XS will be giving a signal to the GS, and also the output signal will be represented by the another arrow here, which is output of the YS. Okay, so this is the signal. This is the signal input. And this is, of course, that is the signal output. So we have the signal input and signal output there. So what about this one? So this one is the functional block, which is the transfer function. All right. And then we have the input. So we have the input, which is the input variable in S plane, in S domain. So input variable here represented by X, and we have the YS, which is the output variable that is represented by YS. So simply for this case, we can say that the ratio of YS to XS is GS, right? So meaning that simply we can take XS times GS at the input, XS times GS, that results in the output of YS. Okay, that is the equation that relates this simple representation of the block diagram that consists of X input, XS as input, and YS as output, and GS is the functional block, which is the transfer function. All right, so in designing or in drawing the block diagram, we also should consider the summing point. Okay, summing point, which is like this. So this is summing positive to negative summing point. So we represent it like that. Let's say if I have A here and this is B signal, all right? So the output of the summing point will be A minus B, okay? So that is the summing point. And also we can also consider another point, which is, for example, if I draw it like this. So what is this? So this is what we call as the branch point. So when we draw a block diagram of the control system, it is not only consists of arrow that represents the signal, this arrow that represents the signal input and the signal output, yeah. But also we also will need to draw some branch point and also the summing point. Okay, that's it. So we have some components that we should consider when we design a control system by using the block diagram. So now let's go back on from the start, from the beginning, from the beginning of this discussion of the topic 2, mathematical modeling. We have been discussing about the equations, differential equation. Okay, so start from there, we try to proceed from another part to another part until we arrive to the design of the block diagram model. Okay, so let us start with how do we follow some of the maybe procedure. Okay, how do we follow the procedure of drawing a block diagram? Let me just write down here the procedure that we can use. The procedure that we can follow, the procedure that we can follow for drawing a block diagram. So when we want to draw a block diagram, we should follow some procedures. So what are the procedures? Okay, put it like this. The procedures we should follow when we want to draw a block diagram. First thing first, what we need to do is when there is a physical system, we write the equation that describe the dynamic behavior of that physical system. Meaning that we try to understand the physical behavior and we try to write each component's equation. Okay, so we start with write the equations that describe, this is too bold, use this one, that describe the dynamic behavior, the dynamic behavior of each component. So in control system block diagram, it has many components. One of them would be some sensors, process, actuators. Okay, I should write again the components, components, components. That's clear. Okay, what's the second procedure? What's the second procedure? Okay, then when we have done with the writing the equations in time domain, for any system, so next step is what we do normally is to take the Laplace transform. Okay, take the Laplace transform of this equation in time domain to Laplace domain, assuming zero initial condition. All right. So second procedure is to take the Laplace transform of this equation assuming zero initial condition. All right. So after we get the equation is in time domain, then we do the Laplace transform to get it as a function of s, and then we assume that that Laplace transformation from time domain to the s domain at the initial time, which is zero, considered as the zero initial condition. Let's say simply we can assume that T naught represented as the initial time during the action, then that T naught is equals to 0. And the third procedure, after we do the Laplace transform, okay, then after that we represent each Laplace transform equation individually in block form. Okay, so after that, when we do the Laplace transform, we represent each Laplace transform equation individually in block form. All right, so we represent each Laplace transform equation, Laplace transform equation individually in block for that for a particular element. So we represent Laplace transform equation individually in the block form. All right, and then number 4, the fourth procedure is after that we assemble the element into a complete block diagram. So the third stage is we try to get the GS and another block HS, another model, and I have Fs, for example, in individual block. Then after that, assemble together to a complete block diagram. Okay, assemble together to a complete block diagram. Let's say, just write it's here. Assemble the elements into a complete block diagram. So we have this sort of Fs, Gs, and Hs. Let's say one of them, Gs represents the, let's say Gs represents the process, actuator something, right? And then Hs represents the controller, for example. And then I have the Fs that represents the sensor. Then we connect everything with the summing point here. Okay, we connect everything using the signal that show the flow of the process. So this is the control system process, okay, that we want to achieve when we design a system. So this is input. So another one, another side is output. Okay. Okay, to make it clear about this, all of this procedure, okay, I'm going to show you based on example, okay, which is the example of the RC circuit. Example, which is in this example, we will try to solve a problem of related to the RC circuit. Okay, so for that RC circuit, let me just draw the RC circuit. Basically, it has R component, R element, and the parallel branch of C capacitor, and also input and output, which is in this case simply the input is the input voltage represented by EI, and also the output voltage represented by E naught. And then this capacitor C and RC. So this is RC circuit that has the input and output. Okay, so we can draw the equation of this system, which is, let's say, the current I, that loop, for that loop, which is the current I can be represented by using output input EI, input voltage, the current at the input EI over R minus the current at the output E naught over R. Okay, so that is the current. So that is the current equation for this particular RC circuit. All right. Now, how about the output part? The output loop. Okay, the output loop. We can also draw the equation of E naught is the voltage across the capacitor, right? So E naught equals to 1 over C integration of current dt. So that is the time domain equation. These two equation is actually the time domain equation. All right. So for that time domain equation, the next step is we want to represent this in the form of Laplace transform. Okay. On the first procedure, we write the equation in time domain, and then we take the Laplace transform of this equation assuming zero initial condition. Okay, so we have that as the first procedure here. So the second procedure, we convert to Laplace domain using the Laplace transform, right? So we have from the first equation, simply in the Laplace domain should be is equals to, so in Laplace domain, make sure that you convert the notation from I kecil ni kepada I besar lah, right? Okay, to the uppercase I. Okay, so EIS EI here, EI is function of S minus E naught is function of S over R lah, over R. So let's say R is same thing lah. So I have IS equals to EIS minus E naught S over R, similar to this one in Laplace domain. So similarly, we can do for the voltage at the output, which is the voltage at the output is E naught, it's function of S. Integration of current, okay, in a Laplace domain, which is IS over C. All right. So a little bit information missing here, which is E naught S here equals to IS over C, not C. So CS. Because when we integrate the capacitor component, I'll show you. Where is it? Where is it? Block diagram. When we integrate the capacitor component, as you can see, in Laplace treble, it's 1 over S. Okay, impulse, let me show you this, which is if we transform the capacitor, here we have UT, which is the voltage across the capacitor, current, IT, we have C capacitance, and in the Laplace transform form for the capacitor is 1 over SC. Okay, so IS become IT become IS lah. So that's it. So that is why we get IS over CS, okay, for the E naught, the voltage across the capacitor. So we have the from these two equations, this is summing operation that we need the summing point. So that the first equation is summing operation. Then, so let's say I want to take this first equation to represent this first equation in the form of block diagram. Okay, so I should have some summing point there, right? And then the block, okay, and then the output, okay. So let's say this is the, at the summing point, let's say this is negative, this is positive. So it is EIS minus E naught, right? So this is EIS function, and bottom one is E naught S function. Okay. What about this block? So it is 1 over R, right? EIS over R minus E naught S over R. So this block supposed to be 1 over R. So what about the output? The output is of course IS. Okay. That is the block that represent the first equation. How about another block that represent this second equation? So I have a 1 over CS block. So I have a block. This is 1 over CS. And we have the output and input. Let's say I put E naught as output. Input is IS. Okay. So bila kita output ni, yang ni adalah transfer function, right? Transfer function that relate the output divided by input. So E naught divided by IS equals to 1 over CS. So 1 over CS is E naught divided by IS based on this equation. Okay, so now what we do is we assemble these two together, which is represent each Laplace transform equation individually in block diagram. Individually, the keywords here individually. For the third one, that is from this equation, we represent individually, which is this one and that one in the form of block diagram. And then we combine, we assemble all together. That is the fourth procedure. Assemble the element into a complete block diagram. All right. So the fourth, this is 3. This is the third. Let me just write the third here. So the fourth procedure is we want to assemble these two block diagrams. Assemble all the individual block diagram representation into one control system block into let's say final control system block into a final control system block. Okay lah. All right. So when we combine that two individual block to one control block diagram, how does it look like? Just simply you redraw this. Okay, we should start with the input of EI as the input. Let's say this is input EI S. So input we have there, and then summing point to 1 over R block. Okay, and then output from 1 over R block is IS, which is the input of the 1 over CS block, and then output of E naught EO or E naught S. That is the output, and then we have the summing point, and we have the junction here. What is that junction called? It is the branch point. We have the branch point as well at the output. So simply this is feedback. This is a feedback signal. Okay, so it should look like this. So when you combine all of this together, it will become the same as the equation that we achieve. So this is E naught actually. So yang ni sama. So summing point tu sama. Oh, sorry, bukan summing point, junction tu sama. Alright. So that is about procedure from the circuit, from the system, how we can draw a block diagram. which is we end up into this sort of block diagram. So next is I'm going to talk about in terms of operation. When we assemble the block diagram, there will be the operation of the block diagram. Let's say we want to simplify some of the blocks, like the cascaded block and also some parallel blocks. Okay, I'm going to show you that. So let me just see what is the next slides here. Okay, so this is just the one of the explanation in the textbook about the DC motor model here. So this is the DC motor model which has the input of VF. Okay, VF as the input and output is theta, which is the rotational displacement theta. So for this particular model of the DC machine can be represented in the form of block diagram that relate the output and input of the system, which is, as you can see here, the process or model of the DC system, also DC motor here, is represented by Km divided by SJS plus B LFS plus RF. So that relates the some of the components here, as you can see, which is this term LFS plus RF is the field variable, magnetic field variable, which is related to the impedance, inductance and resistance there. And also this one, this term JS plus B is related to the load. B is the friction. Bila kita attach load pada motor tu, of course dia akan daripada pusingan yang laju kepada pusingan yang lebih perlahan sebab ada load kan. Okay, so Km is the motor constant lah. So this is the explanation a bit of explanation that relate the block diagram model of the DC machine or DC motor, which is basically based on the cause and effect relationship input and output. Okay. So basically when we deal with the block diagram, we have many blocks, so that we will need to do some simplification or block diagram reduction. So basically, what is the block diagram reduction? This is another information from the buku text, which is the theory. For example, this block diagram has two inputs and two output. We can relate this by using the mathematical equation and rearrange it into so n-dimensional system, for example, and then relate it as a vector and matrix like this. And this is the block diagram model that connects to each other, which is the interconnected system. Okay, and then some block diagram transformations. Okay, so I hope that you can have a check at this, which is if we want to combine block diagram in a cascaded block diagram, it should become like this. Combine these two block menjadi satu, input and output maintain, dan dalam tu function tu akan berubah sikit lah. So yang ni saya akan tunjukkan kemudian lah. So ada dua, yang kedua moving summing point behind a block from this to this, okay. Moving a pick off point ahead of a block from this to this, okay. Kalau kita nak daripada output kita nak movekan dia punya junction tu, okay, ke belakang, dia akan jadi macam ni lah. Moving a pick off point behind a block. Ini daripada belakang nak pergi ke depan. Okay. Ada lagi moving a summing point ahead of a block. Yang daripada macam ni kepada macam ni. And 6 eliminating a feedback loop. Okay. So kita nak eliminate feedback loop jadi macam ni. Okay. So ada example here. You can see how we can use this example of the multiple blocks of transfer function. Kita nak simplifykan, which is we call it as the block diagram reduction lah. Block diagram reduction. Okay. Okay, macam yang ni kan, dia nak pergi ke sana, jadi blok yang kedua, yang ni. Okay, dia langkau ke belakang tu. So nanti have a check apa maksud ni, sehinggalah daripada blok ni menjadi satu blok sahaja. Dia simplify dan a lot of functions in there masuk. Okay, so I hope you can do self-study by referring this figure 2.25 from the textbook, and there will be the description in the textbook that you can follow. Do your self-study on how to do the reduction or block diagram reduction based on the system with multiple block like this until a system with single block with input and output, and what is inside the single block was the transfer function, which looks like more complicated transfer function lah. So what is block diagram reduction here? I'm going to talk about what is the block diagram reduction, a bit of notes here. Okay, block diagram reduction. All right, block diagram reduction. Let's say for simplest example, we can say that, for example, a cascading block are replaced, blok yang banyak tu replace with a single block. Itu yang dinamakan sebagai block diagram reduction. Block diagram reduction. Okay, so what are the benefits of block diagram reduction? So benefit one, it simplify a complicated block diagram dia simplify complicated block diagram with many feedback loops. Dia simplifikan. Okey, maknanya blok diagram yang banyak ni menjadi satu saja. Ni banyak feedback arrow yang ke belakang tu banyak. Bercabang-cabang, banyaklah, lebih daripada satu. Alright. Yang kedua, benefit kedua, simplification. Simplification of the block diagram by arrangement. Ni daripada buku teks by arrangement considerably reduces the labor. Needed for subsequent mathematical analysis. Maknanya simplifikan. Oh, okay. So yang ni, in terms of mathematical analysis ni, lebih simple lah sebab satu blok saja. Tak perlu deal with many blocks. For subsequent mathematical analysis. Alright. So that is the benefits of the block diagram reduction. But there are disadvantages. When simplified to one block, what happened? When we further simplify into one block, what we see here is what is inside the block, which is too complicated. The transfer function here becomes more complex. And then when the transfer function becomes more complex, it should have some more poles and zeros. So there will be new poles and zeros. Yang ni mungkin ada single poles, tak banyak lah. Bila kita simplifykan macam ni, dia akan menyebabkan lebih complicated lah in terms of solving the poles and zeros to analyze the stability of the system. Okay. Alright. But when simplified, when we simplify to one block, the transfer functions becomes more complex. Because new poles and new zeros are generated. Daripada asalnya mungkin satu pole, single poles, single zeros. But when it comes to more complicated transfer function like this, we will expect some more poles and zeros, which is in return will give our analysis more complicated. Okay, more complex because new poles and zeros are generated. That's it. Okay. All right. Next step. Let me do just let we do some proof. Some proof of this. Let's say why is that G1 G2 from this cascaded block? How does it becomes G1 and G2? So let me show some calculation to show you the proof. Let's say if I have a block, cascaded block of F1S, okay, two cascaded block of F1 and F2S, okay, with the input output like that. So let's say I have the input of theta 1. In the middle, we have theta 2, okay, and the output is theta 3. So we want the expression in terms of theta 3 and theta 1. So we want to combine these two cascaded blocks. So by equation, basically, we can draw the equation of theta 2. So using the rational function ataupun ratio of output and input that define the transfer function. Okay, so for this particular block diagram, cascaded block diagram, for the first one here, we can determine theta 2, which is F1S theta 1. All right. So how about the second block here? So we can determine the theta 3, which is equals to F2 as theta 2, right? So here we want to eliminate theta 2. Okay, kita nak combine dua block ni. Of course, kita nak eliminate theta 2. So we rearrange that equation to eliminate theta 2. Okay, so from this equation, substitute saja. So theta 3 of that equation is F2S. So we substitute theta 2. Which is theta 2 is this one. So F1S theta 1. Okay. So we get F1 and F2 lah. Okay. Saya nak letak F1 dulu. F1 dengan F2 S and then theta 1 sama dengan theta 3. So if I take the ratio of output and input, theta 3 divided by theta 1, so equals to F1S F2S. So simply we can redraw the block of this relationship of input and output. So theta 3 at the output, theta 1 at the input. So what is inside the block is F1S, F2S. Okay, what is inside the block is, if we take the ratio of output to the input, inside the block is F1S, F2S. So we have two blocks now represented as a single block. That is the reduction example, the calculation of the block diagram reduction example of a cascaded block. Okay, number 2. So this is number 1. How about number 2 if I have a parallel block with summing point there? I have theta 4 here, which is the output from the first block is theta 2. Okay, and then this block is parallel to another block here. So one output, which is two output, which is same output here. Okay, and the summing point and theta 4 is the output. The input is theta 1, meaning that theta 1 is the input of this block and theta 1 also the input of this block. So we have this transfer function of F1 theta, F1S, F1S for this one, and F2S for the other one. So what we call this as a parallel block. So how do we draw the equations that relates these two blocks in parallel? So that it becomes the no example here. So that it becomes one single block. Let's say for this summing point, sorry, I missed one theta, which is theta 3 is here. So theta 4. So this is summing point of plus and plus. So theta 4 is theta 2 plus theta 3, right? Theta 4 is theta 2 plus theta 3. Okay. Another equation is theta 2 is F1S. Theta 2 ni output. Inputnya adalah theta 1 darab dengan F1S. Okay. And then another equation is theta 3. Similarly, can do for the theta 3. Alright. So here we can substitute this to that. Substitute. So we substitute this equation in that first equation. So that we have theta 4. When we substitute, theta 4 equals to F1S theta 1 plus F2S theta 1 juga lah. Okay, bila kita substitute tu. So we try to rearrange this, put the theta 1 at the beginning in front. So what is inside here is F1S plus F2S. Okay. So then we have, we can take the ratio of theta 4 divided by theta 1 output divided by input. So that it becomes F1S plus F2, F1S plus F2S. Okay, F1S plus F2S. So we can again draw the parallel block as what we see earlier. This parallel block, I can redraw this by taking the relationship of theta 4 divided by theta 1. So I have this block, input and output. Output is theta 4, input is theta 1. So what is inside the block is F1S plus F2S. Okay. So that is the proof of the parallel block. Another example here. The previous example was the feed forward upon forward. Let's say if I have the block with feedback like this. Now summing point is at the beginning. So let's say this one is F1S. This is F2S. Okay. Theta 4 as the output. Theta 2 input to F1. So output of F2S is theta 3 and input theta 1. So summing point plus and minus because this is negative feedback system, right? So for that particular negative feedback system, we do the same thing to prove that, to change this into what I call as the single block, which is this one is related to the number 6, limiting a feedback loop, which is we have this to this. All right. So let me show you on how to do the calculation for this. X2 equals to theta 1 minus theta 3, which is about here. X2 sama dengan theta 1 minus theta 3. Okay. So how about theta 4? Theta 4 here is F1S theta 2, right? How about theta 3? Similarly, we can do for the theta 3, which is F2S theta 4. So here actually, we want ratio of theta 4 by theta 1. So what we do is, so we eliminate, of course we eliminate theta 2 and theta 3. Okay, all right. So how do we eliminate the theta 2 and theta 3? Let's say from here, just take theta 2 equals to theta 4 divided by F1S. Right? Take theta 2. Then we substitute theta 2, which is we have this equation. Theta 2 equals to theta 1 minus theta 3. So, saya terbalikkan. Saya mulakan dengan theta 1 minus theta 3 dulu. Equals to, substitute kepada yang ni lah, equation tadi, which is theta 4 divided by F1S. You can do the same thing. You can do the other way around. When you do the mathematical calculation, you will not lost. Alright. Then, after we substitute theta 2, now we substitute theta 3. Because we want to eliminate the theta 2 and theta 3. Okay. So to eliminate theta 3, we start from this equation. Theta 1 equals to F2S, sorry, theta 1 minus F2S, theta 4 equals to F2S theta 4 is theta 3 ya. So daripada equation yang atas ni ya. Daripada equation yang atas ni, gantikan theta 3. Gantikan theta 3. Jadi theta 1 minus F2S theta 4 equals to theta 4 divided by F1S. Alright. So we have that equation so that we can just rearrange it to do the mathematics. Theta 1 F yang bawah, F1S ni naik ke atas. Di sebelah sana F1S minus F1S F2S theta 4 equals to theta 4, right? Kita tulis elok-elok sikit ya. Oh, tak kemas lah. F2S equals to theta 4. Nampak? Okay, okay ya. Okay, then we rearrange F1S here. Hantar ke sana semua. So, I got this theta 4. Sebab kita nak keluarkan theta 4 lepas ni ya. F1S F2S theta 4, right? So, daripada sini kita boleh keluarkan lah. Kita nak dapatkan ratio theta 4 by theta 1 kan. So, yang ni saya keluarkan theta 4. No, sorry. Kita salah. 1 tambah F1S F2S. Okey, dalam kurungan. So, ini adalah theta 1 F1S. So, then we can take the ratio of theta 4 divided by theta 1. So, kita take the ratio theta 4 divided by theta 1. Menjadi F1S divided by 1 plus F1S F2S, right? So simply for this ratio, this is a new transfer function of single block, of single block of the block with feedback. So I can redraw this back again with just single block. Okay, input and output. Output is theta 4, input is theta 1. Which is inside the block is function of F1S divided by 1 plus F1S F2S. Alright, so this is the simplified diagram. This is the simplified. Okay, of the system with feedback. Okay, so I think that's all to cover about the block diagram reduction, the theory of the block diagram reduction. Maybe I will give some example questions later so that you can familiarize yourself when you do the block diagram reduction. Right? So, okay, I need to finish this session up to this stage. Okay, so thank you. Assalamualaikum warahmatullahi wabarakatuh.